So Ghana needs ventilators to help in critical care for people who have COVID-19 disease. As we speak, there are 4 people in ICUs. We know that in Ghana we have about 67 ventilators. I've come here to Academic City to speak to a professor who says he can build low-cost ventilators to help in our COVID-19 fight. Let's get in there and see what they have for us. So I'm here at the lab to see my good friend, Professor Fred McBagonluri, an inventor. He has over 50 patents to his name. What is he up to? Let's see what he has for us. Fred, how are you? We are greeting with.
We're doing the leg thing, huh?
What is going on? What is this?
Well, we are trying to build a low-cost ventilator in response to this pandemic that is ravaging the whole world. About a week ago, I sent a call out on Facebook for volunteers to come to Academic City College to support the team here to build one. And I have a combination of students here, a student from Ashasi, some second-year students here, as well as some professionals in the medical devices field that responded to the call.
How close are you to building your low-cost ventilator?
Well, we have a prototype that we'll show you soon. I think we have the concepts are done. We have 2 key concepts here. One is already motor-driven, using a typical windshield wiper motor. The second one is a piston-driven one. We're now 3D printing the rack and pinion systems to automate it.
How long did it take you to do?
1 solid week of sleepless nights.
And how much will it cost?
We are hoping that this should, in mass production, should cost about 1,000 cedis.
So can you show me what you have so far?
Sure. I have Mr. Nsemgh here, somebody who has been in the medical devices field for some time now. He's going to take you through the demonstration of the prototype as well as the real biology and physics behind this mechanism.
The physiology behind this is that when the patient has this virus, the coronavirus, some of the lungs are filled with fluid. Some of them are collapsed and some of them are okay. So the idea here is to maintain the ones that are okay and reinflate the ones that have collapsed. So basically we have the air pump here. The air is generated from here. It goes through the humidifier. The humidifier puts moisture in the air because you don't want to be sending dry air to the patient. Then it comes through to the lungs. This is the artificial lungs. Then the patient then expires. Then it goes through the positive end expiratory pressure. This valve is supposed to prevent the lungs from collapsing again, maintaining a positive pressure here. Then from there, it goes through the scrubber, where it contains 70% alcohol to kill the viruses in the expired air before we release it into the atmosphere.
Can you demonstrate how the breathing happens or how the respirator works?
Okay, so basically here you have this pump system, push it up and down, and then air gets filled, and then air gets into the lungs. So this system is going to be tied to a mechanical system which is timed. So it's going to be done automatically. So as it goes up and down, air is pumped into the lungs. This is the artificial lungs. Here, behind here, we have the humidifier. Here we have the PEEP. That is the positive end expiratory pressure valve. And here we have the scrubber. So these 4 main parts make up the basic ventilator. So based on its operation, the pump will be coupled to a mechanism here to do the automatic pumping. So it will move up and down. So as it's being pumped, the lungs are being filled. As it's being pumped, the lungs are being filled. Then when the lungs are filled, during the patient will have to expire the air out. So during the expiratory phase, the air goes through the PEEP system, which prevents the lungs from collapsing, and then goes through the scrubber, which kills the viruses before the expired air is emitted into the environment. So basically, that is how it works.
What is left for this to work?
So currently we are 3D printing the rack and pinion system to do the automatic pumping. So currently that is what is left to complete the first prototype of this version.
And if, touch wood, we have 2,000 cases and there are so many people who need respirators and we don't have enough, can this work in a normal hospital where somebody is under intensive care, or do they need to spruce it up for it to work?
So, when we started this, the whole concept was to come up with something that functions in resource-limited environment. So, as he indicated, with the manual piston action, if you are in an environment where you are desperate to care for somebody, I'm sure family members will not mind taking turns to pump this thing. Okay, so there's no electronics needed here. If you are in an advanced intensive care unit, you can remove this pump action and replace it with an oxygen canister. The way we've also designed it has a little bit of agility in it, so you can actually configure 4 of these at the same time. They could be using the same oxygen source, they could be using the same humidifier source, they could be using the same scrubber source, and then you can move them on wheels into an intensive care unit. So think about a field unit. So it's light, portable, and very agile, and we're taking into consideration both. So we can put electronics in here to make it as sophisticated as the ones that we buy from abroad, or as simple and agile enough to be used in remote areas. And then we're also thinking solar. We could also have a solar configuration here where you can use it in the field.
So those are all add-ons, but the basic that you need is here.
It's here, that's correct. So the basic concept is here.
It took you 1 week to do this. Yeah. So let's assume we need 50. Yeah. What would it take to produce 50? Because you're saying this could cost us about 1,000 cedis. Yes. So assuming the government said we need 50 to send to the Upper East region by next 2 weeks, how are you going to do the 50?
So next 2 weeks it won't happen. I say that because we're going to have to source real components. So all these PVC pipes you see here have to be transparent so that you can see the liquid. They have to be graduated so that you can see the volumes. You have to be able to track how much air is being delivered to the patient. So at a conceptual level, this works. But we need to go through the second stage of productization, where you actually turn it into a product and then you have to validate it to make sure that you can actually put it on the patient. But when we complete this, I don't think it will take more than 20 to 25 minutes to assemble one.
When you complete the productization, yes, it will not take you 20 to 25 minutes to build one.
Yes, that's correct. Because the parts are really simple. There's a series of fittings and tubes. And so design for assembly is also one of the cost factors in building very agile systems. So I think a trained technician should be able to do this within 20 to 25 minutes to assemble one.
And can this be built anywhere, or you need a lab like this to do it?
This can be done anywhere. You can actually send the components to the field and have them assemble in real time.
So the main issue is the productization. Can you explain what that means and how long that takes?
Yes. So productization basically means that, the basic physics, the basic chemistry, the basic biology behind a product has been validated. And then you build a prototype, you test the prototype, which we've done here, to make sure that all the parts are working, functioning properly. You can demonstrate that, you can actually feel along. And then you go to productizing, which means that now you have to source real components, assemble the system, package it nicely the way it will look like in the field, and then you subject it to the FDA test for a medical device to make sure that people's lives are not endangered. You put it on a dummy first to test the dummy, make sure the dummy can inhale and exhale with the help of the pump, and then you do a few human subjects tests. And then
can't we cut short that process? I mean, we are planning for a spike, yes, based on the projections. Yes. If a hospital comes to you and says, look, we don't have $55,000 to buy a ventilator and we want you to do something for us, which of the processes can we cut short, and what do you need to happen for you to move quicker to production?
I would say, a letter from Ghana Standard Board or FDA saying, look, the basic biology is replicated by your system. Let's put it in 25 people and see how it works, and if it functions, let's deploy it. So it's a policy, it's more of a regulatory and policy issue.
So if I go to Professor Dodu and I said, Professor McBagonluri of Academic City has a prototype ventilator, he needs to come here, look at it, and then within a week or two, he can tell you whether this is good enough to be used in a hospital.
Yes, absolutely. That's all he has to. He has to have confidence that we're not going to have mortalities when we use this system. But this is basically, I mean, the basic functions of a typical hospital ventilator is here, mechanized.
So there you have it. The concept is there. Standards Authority has to come and check it out. We'll call Professor Adodu to see what he thinks about this. But he's going to show us a few more things that they are doing. I'm told they are different concepts. So let's check out what he has again.
So this is the second prototype that we developed. In fact, this was the first prototype that we put together. And it's made from locally available repurposed material. So the mechanism here is based on a typical windshield wiper blade motor. It is actually a windshield mechanical motor. And this is a Ford, came from a Ford. And this bellows was built from just your typical leather. So when you go to a blacksmith shop, there's always somebody sitting down there pushing on this leather, generating air into the bellows. Okay? So that's the same concept here. This mechanism pushes against these bellows. We create the air goes into the humidifier. Then from the humidifier, it goes into the patient, comes out, goes into the PIP system, and then goes out into the scrubber. So the mechanism is the same, just that this is an alternate air source that we have over here. Okay. So if you bring your hand over here, this bad boy is producing. Okay.
So you connect the pipes here.
You connect the pipes here.
What is this?
So that's a car battery, and the electronic system here is basically power electronics to control the speed of this motor and also to prevent it from overheating. Now, in the next stages of our development, we actually connect a pressure sensor to the patient and also monitor the pressure sensor so that when the patients begin to breathe on their own, we don't flood them with air so that they drown in air. And that's one of the critical things you need to take into consideration when designing vents. Because when the lungs are collapsed completely and the patient cannot breathe, the mechanical vent helps them to resuscitate. And then once they start breathing, the system has to know that the patient is breathing now so that it will synchronize with the breathing cycle. Otherwise, you're going to be pushing air into them while they are pushing air out, and you could kill the patient.
How long did it take you to do this?
I think it was a day that we put the concept together, but then trying to make sure that it's working right, it's pushing out the right side. So these two prototypes were actually done in a week.
The first one looks more like your typical respirator than this one.
Yes.
But which is cheaper?
That one will be cheaper.
That one will be cheaper?
Yes, that one will be cheaper because the control mechanism is less expensive. This could cost you 500 cedis easily, just the motor itself.
Which one can you do faster?
We can do that one faster.
Yeah. Super.
Yeah. So do you guys want to talk a little bit about electronics here, what you're doing here?
Just for record, yes.
Hello, I'm Barnabas Nomo, second year in Academic City. I'm studying computer engineering. And so I've been working with Nathaniel here on the controls. And so far we've been able to get the motor control set up. We use the motor driver connected with a relay just to give it a higher edge of current. And we are waiting for a shipment of pressure sensors this week. And so when the pressure sensors should arrive, we'll be able to connect them in such that the motors go into a more reactive mode so that it syncs with when the person starts to breathe. And so aside that, we also realized that we need to put some cooling on here because the amount of power required to move this motor causes a lot of heating. So those are things that we've had to figure out over the course of the week as we were building. So Nat, will you?
Okay. We are trying to model a 3D version of the ventilator. So from the computer here, this is the hardware of the ventilator, which we are later going to print out and using the 3D printer. And on the projector, we can see that these are the racks where the cylinders are going to sit, the racks for the cylinders for the ventilator. So yeah, and we are trying to figure out the dimensions that will be needed to build the whole ventilator so that we can really have a functional unit.
Okay, so this one is like the clamp where the other pipes will go in. So the pipes are actually 4, but this is for 3 of the pipes that are at the same level. We are yet to do the other one for the longer pipe.